see. All right, so today I'm going to be talking about SSRF, server-side request forgery vulnerabilities, and some very fun things that you can do with this. This is, as you may notice, there are two names on there and only one person up here. This is a talk that I did with my coworker and collaborator, Ben Sadiqapur. But I'm going to go through it just myself for this one. So just a quick introduction to who we, and especially me, are in this case. I head up hacker education at HackerOne. So if you've seen the site Hacker 101, where anyone can learn everything from the basics of web hacking up through mobile and native hacking, reverse engineering, that's my baby. I worked on hacking hotel logs, released that back in Black Hat, hacked between 4 and 10 million hotel logs, hacked the Nintendo Switch, iTunes, a couple other things. And you can find me on Twitter at Dakin. So let's jump right in. What is SSRF? So SSRF is server-side request forgery. And essentially what that means is you're telling the server, okay, I want to fetch this resource from somewhere. You give it a URL, it goes out, grabs that, it might process it and show you nothing. It might grab it and then show you exactly what you just told it to grab, any number of things. In the simplest cases, these are just absolutely trivial bugs to exploit. You know, you might just give it a URL, it'll go, oh great, I got that data. Here's the data that I got, here's everything that you need to know about it. And then you can access any internal services that are on its network, whether that's a lot of NoSQL databases expose themselves over HTTP, internal services that you may want to hit that are custom to a company, metadata services, we're going to be talking a lot about those. Those are all things that you can hit with SSRF. So basically the TLDR is you're going to make a request to some target, and in some cases, the ones that are most fun, and we're going to talk about how that happens, we'll actually have JavaScript just executing on a server, and usually not a confined enough way. So cloud metadata is something that we're going to be talking about a lot. Typically what it's going to be is some service that's at 169.254, 169.254. That's what it is for Google, Google Cloud. That's what it is for Amazon, EC2 and ECS. That's what it is for Azure. Pretty much all of them just use the same IP. And it just sits there listening on plain HTTP, and it'll provide, innocuous things like what the name of the project is, what the host name of the server is, things like that. It also provides slightly less innocuous things like SSH keys or AWS access keys and secret keys. Pretty much anything that you need to own the project entirely can come straight from the metadata service. Or you can push data up to it. There's a lot of stuff that you can do with it that's fun. But that's basically that. In 2019, if you're able to hit that IP from that side, you're able to hit it from the context of that server, it's game over. Like there's just no way around it. Oops. So a basic example here would be, let's say you can upload an avatar to a site. You tell it to go fetch this URL. You give it, whatever site that you're going to hit. And if you change that URL parameter to something internal, it may go get that, pull it down as an image, and just render that straight to the browser. What's fun about a lot of those cases is that you're not just limited to hitting HTTP. You might be able to open up files and just read arbitrary files off the disk. You may be able to make it, make requests on other protocols like making FTP connections or HTTP and automatically passing credentials, things like that. There are a lot of interesting routes there, but for this one we're going to talk primarily about HTTP, just because a lot of the other ones have been kind of well trod over the last 20 years. There we go. So there are two quick CVEs that I'd like to talk about. So one was a Jira bug back in 2017 that if you find Jira instances that you can hit today, there's still a pretty damn good chance that you're actually going to find this bug, which is mildly terrifying. And it works basically like that trivial example where you just give it an icon URI and just say consumer URI equals Google, and it just hands you back whatever the hell it gets. It's absolutely trivial, and it's something you'll still see today. So here you can see pulling from the metadata service 169.254, et cetera. And same thing with Jenkins. Jenkins last year had a fairly close bug where you could go and pull any of the metadata services, any URL. You could just make a request. You could only make GET requests, which limits you in certain capacities. But at the end of the day, for the vast majority of Jenkins installations, this was an absolute game over, pack it up, go home situation. And again, it's another one that you can still find out there way too often. So what we've talked about so far are the trivial SSRF. Like these are a single HTTP request. They just hand you the data. Maybe it's not everything. Maybe they're parsing out certain bits of it or whatever. But usually those are pretty straightforward. But those aren't the really interesting ones. And those are things that people have talked about a lot as those straightforward ones. But there are a lot of options for the less straightforward ones. So for instance, one of the major problems is that metadata or internal IPs get filtered. Like it just won't take an IP. Conveniently, if you just do awsmd.ssrftest.com, it resolves to the exact same IP. And if they're not actually resolving what the host names are that you're accessing, you just get right in. If you can only use whitelisted domains, you have the option to find an open redirect on there and redirect to those metadata services or other internal services. If the SSRF is there, but you can't see the output in any capacity, you have a couple different routes. One of the easiest is to use JavaScript and exfiltrate the data. And you'll see why JavaScript would run in this context at all in just a moment. Another option that you have is almost an XXE style where you're chaining requests together so that it's making a request to one server and then handing the data off to another. Those get a little messy, but they do pop up from time to time, and I can show you some examples after the talk if you're curious. So one of the things that I've been looking at for the last year and what actually spawned this talk was XSS leading to SSRF. So if you have things like PDF generators, which we're going to talk about in much greater detail here, oftentimes they're just taking HTML and converting it over to a PDF, which happens in a couple different ways. But oftentimes you can just get straight JavaScript executing in the context of a server via that. You also can have a number of redirection style bugs where it's attempting to go fetch a certain page to render to a PDF. You can redirect it over to one of those metadata pages, things like that. So PDF generation is really interesting in the context of SSRF because it just gives you so much power as an attacker. There's so many fun ways that it breaks. So one of the routes is headless browsers. These are exactly what they sound like. So you have things like WKHTML to PDF, which is literally just WebKit, where instead of rendering to the screen, using 3D acceleration and all that, it renders to a PDF. Headless Chrome is literally just desktop Chrome minus the GUI, and instead of their backend rendering to the hardware, it renders to a PDF or an image. Headless Chrome is sandboxed. It has all the same protections that standard desktop Chrome has. It is very hard to break, except when you're generating PDFs. There are some really interesting things there. And what's really convenient about these for the developers is there are wrappers for all of this. Like you can, no matter what language you're using, you're going to get a simple integration here and be able to implement this in your application in minutes. The other option for doing PDF generation these days, because nobody wants to generate PDFs directly. It's hard. You have to duplicate all of your style work. You're going to end up creating entirely new templates just to create PDFs rather than using the HTML and CSS that you've already generated. So one of the other options here is to use an HTML renderer. Things like Wheezy Print are common ones. That's a Python library that just literally parses in HTML and some basic CSS, does the layout stuff, and then spits out a PDF. What sucks about this from an attacker perspective is that it's very limited. You have no JavaScript. You don't have real CSS. There's not a whole lot of magic that you can do there. Only certain tags are going to be supported. These work well for doing simple, invoices and other things like that in applications. But they're very limited, and they make it a problem for attackers. So as I said, most of the time you're not generating PDFs directly. It does happen, I would say about 1/8 of the time in the applications that I test. But most of the time you're just spitting out HTML. And what's great about that is that if you have XSS into that HTML, if you're able to get any kind of script tag or an iframe in there, things like that, you're not running on the client. You're running on the server. You are running there where you can do whatever the browser is able to do in their world. You're able to control it from their side. How you actually go about attacking that is going to depend on what that category of attack is, either that is headless browsers or HTML renderers. So you notice that you have HTML rendering, inside of a PDF. How do we actually see that it's doing something with that? So we can actually just usually put in an iframe or even an image source, point it to some host that you control, and if you just run netcat on there, you'll see a connection where it just handily tells you WK-HTML Linux AMD64. And then you know exactly what engine you're up against. You can figure out what your target is. And if you go ahead and you just throw in that user data endpoint for Amazon AWS, once you've seen where it's coming from, you're going to know exactly what it's hosted on and all that. You're just going to get it to spit out the access key ID and the secret access key. If they haven't set their permissions perfectly in AWS, this will allow you to spin up instances, access any of the instances, access all of their data stores in S3, all of that stuff just using this data that's dumped out from that iframe, and it just goes right into your PDF. So that's the trivial case, and that's what you always hope for. You hope that it's just going to be that one and done, put in the iframe, it loads, perfect. Unfortunately, that's not how that tends to go, or fortunately, because I like the challenge. Headless Chrome, as I said, is just desktop Chrome with a different rendering backend. And that means that you have to worry about things like same origin policy. You have to worry about the fact that if you load an iframe in it, it's not going to load a plain text HTTP resource if it's loading from an HTTPS context, which is often what happens with invoice applications and things like that. If you do a redirect, it sees, oh, I finished loading the first page. I'm going to kill it and render that. So you can't redirect off to, just a different page that's there. So this kind of makes it so that you're trying to exploit it much like you would, if you were accessing somebody's router from their browser, via XSS. There's just not a whole lot that you can do with it, because it's a browser, and browsers, well, Google puts a lot of money into making sure that stuff isn't easy. One of the things to point out is, if you have, if let's say you have an application that takes in some styles, you're able to theme these invoices, was the actual case here. In this case, we were able to escape the style tag because we were able to control, I believe it was the font color, or the font style. So just using Helvetica closing tag style was able to actually break the PDF and get us in there so that we had XSS. Slide is slightly out of order there. So in this case, we confirm that it renders HTML in there. And we see that it's making a request to our site using Java. It's fetching this image from our domain. So what actually happens here? Well, in this case, if we just replace that with closing tag style iframe source user data, we get those secret access keys. So that's again that trivial case. Now, Wheezy Print was a fun one. Wheezy Print was one, we actually were hacking a rideshare app where at the end of the ride, you could put in a reason for an expense. So if you were using it in a commercial context, you could put in what the reason for that ride was so you could expense it through your company. So we noticed that there was cross-site scripting in here into a PDF, but we had no idea what we were doing. It was entirely through a mobile app, and we had to take a ride share every single time we wanted to test this thing. So for every single payload that we wanted to do, we had to actually take a ride. And I think our total was something like 13 throughout New York City over the course of a couple days. Well, this one actually did take a while though. Like it was a couple days in New York, but this was, I think, 3 months after the bug was actually first discovered. My colleague found the bug, had no idea what to do with it, but knew that there was something there. Like he just had that spidey sense of, I know that I can do something. But once we were in there, like we couldn't run any scripts, we couldn't get any iframes. They just showed a almost like a Netscape broken image type thing. It would load images, but that was it. Unless it was a valid image, it was screwed. And as I said, every single payload was a ride share. Got expensive quick. But once we got this actually working, we got it to talk to a server and just request an image. That's all we cared about, was make a request for an image. And we saw that it was Wheezy Print, which at the time we had never heard of. Did a Google search for it, found out it's just an open source Python library. And at that point, we could actually take a step back, write a little test harness that made it look like that environment, and be able to generate PDFs just like they were doing. So we could test in our environment instead of racking up rides on the service. But this was where I kind of I despaired. I spent a good 12 hours looking through the source, looking at what it could do, and it seemed like there was nothing interesting to this at all. So in terms of actually using this, you can literally just install the Wheezy Print utility and just give it some HTML and give it an output, and it does the thing. But we were doing things like this, of, a script of a document write, we did an image source, we did an iframe source, and it just did nothing. So we looked at the actual html.py file in the repo, and we saw that we have images, and I actually started going down the path of okay, it loads these images using GDK. Maybe there's a vulnerability there. Maybe there's some old CVE that just isn't patched. Who knows? Maybe there's something, and I'm going to end up, doing some memory corruption insanity. But I, really didn't want to go down that path. There was embed, but it just ended up going to the same exact path. Same thing with object. They all just loaded images and super limited at that. But then I saw that there was this parser for a link tag. And that just seemed unusual. If we want links, we just use A, right? Well, turns out that in Wheezy Print, there's a very fun function where you can literally just tell it to go fetch a URI. And what happens is it doesn't actually show you on the page. You see nothing when this happens. So even if you're looking at the PDFs, you don't see anything. PDFs can have multiple data streams, and it will embed whatever it fetched as a data stream in the PDF. So, of course, the first thing we did is read Etsy password. We had to do this. We knew that we had to. But we also could make web requests. So we did one ride share to read Etsy password. We did one ride share to get the username for AWS. And then one more ride share to actually pull their secret access key using that username. And yeah, we just wrote a little script that would pull it out. It's just zlib deflated data. You just hand it a PDF and boom, it pulls out that whatever file was in there. So that was a really fun one. We actually are still, that was back in November. We're still working with the company to get permission, because we actually had videographers following us for the entire thing, because it was during one of HackerOne's live hacking events, and they just happened to be around and it seemed interesting. So we have professional video of all this stuff, and one day we're going to get to release that. But let's talk about DNS rebinding and actually a proof of concept that I can show you that was really cool. So same origin policy like I talked about before makes things really difficult when you're actually trying to fetch some random host. If you're on exploit.info and you try to make an XML HTTP request from JavaScript to 169.254, et cetera, it's going to fail. The browser is going to say, no, you don't have permission to do this. This is not a thing that you're allowed to do. That's standard browser security that we've all known about. But of course it can make XML HTTP requests to itself. Like its own domain is safe. It's secure. It knows that it loaded the code from there, so of course it can make requests to there. How can that go wrong? Well, here's how it can go wrong. So let's say that the browser actually does load that x.ploit.info. When it loads, the script tells the server, okay, I'm here, I've loaded, rebind. And the DNS server on the other side says, okay, exploit.info is now 169.254, et cetera. At this point, the browser, if it tries making requests to exploit info, is still going to hit the original server. The reason is that Chrome has its own DNS cache, but it's only limited to 2,500 entries. So if we just open a0.exploit.info through a2499.exploit.info, we just blow away the entire damn DNS cache. And now whatever request we make is going to make a new DNS request. So it goes ahead, it makes a request to exploit.info, and it suddenly sees, okay, I'm here. I can actually make any request whatsoever to the metadata service. The metadata service doesn't look at its host field. Possibly something they should do in the future. I think that's going to be a change that they're going to make. But they don't look at the host field. They don't care where you're coming from. As long as you're able to hit it, it doesn't matter. And of course, we keep bc.exploit.info as a back channel for exfiltration. And by the way, x.ploit.info is actually a domain that I bought for this attack because I couldn't resist. But we have a back channel so that we can actually keep that mapped to the same server, and we can just send up log messages. So anything that we pull, the progress through the attack, all of that goes to that same host. And here, I can actually demonstrate a fun little proof of concept using this exact attack. And this is on Snapchat. So Snapchat ad program, they have the ability to add these brand logos. And of course you would think that they would just like maybe take a URL for an image and maybe fetch that. No, they go ham. They actually go and make a request to whatever server it is, run the HTML, and then pull image tags out of it. So if there's any JavaScript that spits images out into it, it just it goes there. So we just intercept that request or repeat that request, change google.com to at this point it was daemon.dakin.dev. We just go ahead and we tell it to make that request. And running on that server, we can see, okay, we triggered in this place, and it's just going to loop. This was before I figured out the cache stuff, so it took a little bit longer. But I actually just repoint that domain to 169, and then wait a few seconds. Okay, it was actually more than a few when you didn't have 20x speed. But this, if I could actually zoom in here, maybe I can. It actually shows you the SSH keys, the host name, everything for that instance because it was running on Google Cloud. We actually got full control over a large part of Snapchat's environment and found this exact thing on their dev environment as well and got even more access. And this was all done via that DNS rebinding attack. So the way that I showed you earlier with like the Python script and then having to change it in Cloudflare and wait for a while, that sucked. It was fraught with difficulty. So I made a script that actually combines a DNS server and an HTTP server. You have to have a domain that you can point its name servers to a server that you control. But if you run this, it actually will work against any headless browser. It'll pop GCP, AWS, and Azure automatically. I'm sure we're going to be adding more later. It runs in less than 2 seconds due to the DNS cache poisoning attack or cache flushing attack. And it's all open source. You can literally just tell it what your target is, like what environment it should be, testing against, whether that's AWS or whatever. And it just does it. It just goes and handles this rebinding attack automatically, because it does combine that DNS and HTTP server together. Very poorly documented at the moment. Like, this was something that I threw together right after the initial talk for this, actually making it public rather than just something I was running. So if anyone wants to help out and contribute there and make it a little bit nicer to use, I'd appreciate the help. But it's all up on GitHub, super useful. This tool at this point has like $40,000 in bounties behind it just in the last couple months. And there's another really useful tool, I'm biased, I wrote this one too, that is useful for SSRF, where it automatically, you can set up buckets for different projects, and it'll give you a unique URL. If something hits that, it will automatically log all the requests, as well as try to do some basic JavaScript exfiltration. So if JavaScript will run, it'll, log that JavaScript is running, which is a useful thing to know. It'll also try to pull EC2 and I think Azure keys, but it's really not great just because same origin policy blocks it in 99% of cases. But this is how if I'm testing to see if something is vulnerable at all to SSRF test, or SSRF, this is how I do it. You can find the source code up on GitHub. You can also just use my instance if you trust my server, and then I'm not gonna go try to steal your bugs. You can do it at ssrftest.com. All free, and pretty easy to use. So a quick recap, SSRFs are dangerous. In my opinion, they are the most dangerous bug that's out there right now in terms of just broad scope. I've found them everywhere. I think between myself and Homsec, my collaborator, I think we're up over 75,000 in bounties, and we both hack at most 1 day a week, just from SSRF over the last year. They're everywhere. Especially if you look at finance apps. They just for a while there, I only looked at invoicing apps because I knew that every single one of them was going to be vulnerable. One of the things to note is don't give up on your bugs. If you see an SSRF of any form, there's a pretty damn good chance that you're going to be able to exploit it to a critical level or multiple different critical levels. Out of probably 40 or 50 SSRF bugs that I found total over the last year, maybe 1 or 2 of them weren't exploitable. One in particular still haunts me to this day. I'm still confident that it is somehow exploitable, and I just haven't figured it out. But don't give up on them. And if you do have something where if you're able to run JavaScript especially, don't just report that bug without figuring out the impact, because you're not going to get paid for it, and 2, they're not going to understand what's really happening there, and they're not going to fix it effectively. If you see a PDF generator somewhere, 9 times out of 10 it's vulnerable. I would bet good money on it anytime I see a PDF generator. Nobody does them from scratch anymore. They just do it via HTML. So if you're able to chain any other vulnerabilities with it, if you're able to get an XSS into it, you're going to be able to pop that thing. In terms of the Defender side, don't run JavaScript in the cloud. If it's your own JavaScript, go for it. Node is a thing. But if you're running arbitrary JavaScript from random attackers, you're basically just printing money for them. Just don't do it. Do whitelisting. Don't blacklist. If you try to blacklist domains, if you blacklist 169.254, etc., I'm just going to go in via IPv6. Don't blacklist, whitelist, and be very strict about it. And make sure that you actually do that effectively. Make sure that if I redirect from a domain that you are fine with over to the metadata service, that you're checking it at each redirect, that you're actually resolving the host that you're hitting, etc. Configure your cloud instances to minimize impact. Make sure that you're actually handling your roles properly. So the role for the Snapchat ad server should not have access to the S3 bucket that has user data in it. That's just a thing that it should not do. And you can also firewall off these internal services, especially if you are knowing that you're taking untrusted data and you're handling that in various ways. And finally, be nice to hackers, like work with them. I don't think I have to tell anybody in this room that. Work with them, be kind to your hackers, and they will be kind to you. They'll continue to find good bugs and keep your users safe. So that's about it. I am on Twitter at Dakin. You can also find me on the Hacker 101 Discord. If you go to hacker101.com, there's a Discord link at the top. I'm always there. We have like 8,500 amazing hackers now that just want to work together and learn and break stuff. So thank you for watching and being here.